Okay, thanks very much. So first of all, I wanted to thank for the opportunity to give a talk here. And this talk will be based on quite a few papers that I've written throughout the years, but I'll try to review the kind of salient points and mostly focusing on the recent results from this year. I'll be talking about integrable sigma models in two-dimensional space. And the main point is that there is so there are several points. So one point is that there is a nice differential geometric setup in which to describe these models. And secondly, there's also some maybe unconventional rewriting of these models that I hope will be of use for the future. So mostly, well, it's kind of a working title that it's about flag manifold sigma models. It's not only about flag manifold sigma models, but that's kind of a general wide class of models that one can study here. So I will explain what these are. And maybe I will start from the most interesting physical application of these models is in the continuum limit of spin chains. And then I will get somewhat more abstract towards the end, explaining this differential geometric setup that I promised. So I'll present some gauge linear formulations for these models, and one of the main points that I would want to convey is that these are the same as gauged chiral bosonic Gros-Neveu models in two dimensions. Yeah. Then this reformulation allows one to study the renormalization group equations for these models in a very simple way. And I will claim that the so-called integrability anomalies in these models that have been known since the 80s, they actually have a simple interpretation in terms of chiral anomalies in these models. And then, actually, the presence of these chiral anomalies, or more exactly the necessity to cancel them, will lead to the introduction of fermions, both supersymmetrically and non-supersymmetrically, and there is again a unifying description of how this can be done. The main property of the target spaces of the models is that they will be complex homogeneous spaces. A wide subclass of these models are flag manifolds. So these are the simplest definition is that these are these homogeneous spaces, SUN divided by S of U and 1 U and S, such that the sum of n's is n from the numerator. There are also some other definitions of what a flag manifold is. For example, if you open some complex geometry textbook, it tells you that it's quotient of a general linear complex group by a parabolic subgroup, which stabilizes a given flag. So a flag is a sequence of a nested sequence of subspaces, linear subspaces in Cn. And there is a relation between these two definitions, which corresponds to picking a complex structure on this flag manifold, which is really the ordering of these n1 and s integers here. Because the relation is that the dimensions of these nested complex flags are the partial sums of these n's. And in which order you take the partial sums, that's basically the complex structure. That's additional data that you have to pick. And mostly it will be about symmetry groups like SUN symmetry group, but it can be generalized to other groups, just that I won't talk about that. Okay, so the first application goes back to the so-called Haldane limit of spin chains. So actually Haldane in the 80s obtained a certain limit of a semi-classical limit of an Heisenberg spin chain near the antiferromagnetic vacuum configuration, which leads to a CP1 sigma model. So sigma model with target space the sphere. So that's kind of a famous result of Haldane. One of the reasons he was given a Nobel Prize also some years ago. This was, so I generalized this in 8 or 9 years ago to the case of SUN. And the main point here, why flag manifolds arise, so as a result, I get flag manifold sigma models. So the reason flag manifolds arise is rather simple. So if you think about the usual classical Heisenberg chain with unit vectors at each side, then this is the Niel state. And the moduli space of Niel states is a sphere, because you have these two anti-linear vectors, but they can rotate around the sphere anywhere you like. So that's the point is that the target space of the sigma model is always this moduli space of Niel vacua. So if you rewrite these antiparallel vectors in complex notation, so if you do a stereographic projection, you just it's the same as having two-dimensional complex vectors orthogonal to each other. That's just a simple fact. So, for example, if you want to pass to SU3 and you have to consider triplets of vectors, all pairwise orthogonal, at 3 consecutive nodes. So the elementary cell of the spin chain has to extend, And you have to impose orthogonality at 3 consecutive nodes, and the configuration space of triples of orthogonal vectors is the flag manifold. And you can also consider, in this way, you can also obtain partial flag manifolds, and in the case of SUN, you just extend this to n sides, and so on and so forth. So, some years ago, this was further extended, this research was further extended in these papers, where the authors studied more carefully the spin chains. They actually found generalizations of Haldane conjectures for this SUN case, and so on. And the nice thing, from the point of view of field theory of these flag manifold models, is that there are these discrete Hopf anomalies in these models, which, so these are some anomalies in discrete symmetries of these models, and in certain cases, the presence of these anomalies predicts gapless behavior, so no gap on the spectrum, for certain representations of the chains. And this matches with rigorous spin chain results from many years ago, actually from 60s and 80s. So this is a nice field theoretic match against some spin chain results. Okay, but in this talk I actually want to focus mostly on integrable models. And now I will pass to the definition of these integrable models, in particular with flag manifold target spaces. So the interesting point about these models is that in general, these are not symmetric spaces. So flag manifolds are not symmetric spaces, and therefore this goes beyond the standard situation studied in the late 70s by many authors, where it was shown that the harmonic maps or solutions of equations of motion of sigma models with symmetric target spaces are integrable. So how do we generalize the situation? So we start with a standard kind of approach. We introduce a Maurer-Cartan current or one form. And we have to introduce the metric and the B field of the sigma model as usual. So in principle, this is summarized by the usual action here. So U are some complex coordinates on the target space. And you see, you might think that this just incorporates the metric here, but actually this presentation already picks a certain B field as well. This is the B field, which is the fundamental Hermitian form of the metric. So a contraction of the metric with a complex structure. Because if you symmetrize this U and U bar, you get the metric, and you anti-symmetrize U and U bar, you get the B field, which is formally given by the same coefficients as the metric. So the metric that you have to take here is the Keeling metric. So just the trace of this projection of the Maurer-Cartan current squared. So that's the simplest kind of metric you can think of. But the interesting thing is that this metric in general is not Kähler metric. So it's well known that flag manifolds are Kähler manifolds, so it's a bit surprising that the metric is not Kähler. But the point is that on these manifolds you have huge families of metrics, and Kähler metrics are just some small subfamilies. So and these are not the ones that you should take if you want to have integrability properties. Well, one hint why this is the correct metric is that, for example, the geodesic motion is automatically integrable for such metrics. So the geodesics are homogeneous. They are one parameter. They are orbits of one parameter subgroups, just of the symmetry group. So anyway, this is just the formal definition of the model. Now I will present some various rewritings of this model that are more illuminating, I think. Okay, yeah, even before I present those rewritings, first I formulate this as a gauge linear sigma model. So gauge linear sigma models, they're quite useful tools. Instead of having nonlinear target space, you have kind of a linear target space with some gauge fields and some quadratic constraints like this. So this goes back to the 70s for the case of Grassmannians. This is the same as so-called Kähler quotient. So you just take a M by N matrix U with a gauge field, with a UM gauge field A. And you write this kind of Lagrangian. And if you eliminate the auxiliary field A, you get the nonlinear sigma model with target space Grassmannian in this case. But actually it's much more useful not to eliminate the gauge field and just work with it as a semi-linear model. Well, semi-linear because you still have this quadratic constraint, which is usually known as the moment map constraint. It just says that the vectors are orthonormal. The vectors inside U are orthonormal. So if I want to generalize this to the case of flag manifolds, this can be done in several ways, depending what kind of metric you want to build, what kind of sigma model you have, what is the metric of the sigma model. So if the metric was Kähler, then the corresponding gauge linear sigma model representation follows from the so-called Nakajima quiver varieties. So these flag manifolds are Nakajima quiver varieties, given by this Nakajima quiver. So Nakajima quiver varieties are some wide class of hyperkähler actually manifolds that includes moduli spaces of instantons and so on, many other interesting varieties, but the flag manifolds are also part of those. More exactly, the cotangent bundles to flag manifolds, but okay, here I just omit this detail. But as I said, the metric that I have is not Kähler, so actually this construction doesn't apply directly. And actually what works in this case is that you take the same Lagrangian, and you plug in, instead of the general gauge field, you plug in this step gauge field. There are zeros here, and the steps, the dimensions of the steps are like the dimensions of the steps in the flag. So D1, D2, and so on, dimensions of the complex subspaces. So in principle, the same model that I wrote on the previous slide can be written like this. You have this M, which is ds minus 1 vectors, orthonormal, with this gauge field, which is the same Lagrangian. Okay, but now there will be another rephrasing of these models. I think maybe simpler one. So actually, it's a combination of this gauge linear sigma model approach from previous slide and the Costello-Yamazaki approach from previous year, where they showed that the sigma models can be written as a coupling of so-called beta-gamma systems. So beta-gamma systems are some field theories in kind of first-order formalism, so they have this kind of action. Well, the claim is that all these models, all these flag manifold models, so I should maybe say that flag manifold models include CPN model, Grassmannian model, all these well-known models. They're actually examples of chiral gauged Gros-Neveu models in bosonic incarnation. So actually, the Lagrangian is just this. This is a chiral gauged Gros-Neveu model, known from the 70s. But usually here in the 70s, people studied the situation where this was a fermion here. So here I call it a Dirac boson. So this is a bosonic variable that looks like a fermion. But the Lagrangian is exactly the same. And the R matrix here, the vertex here is given by the R matrix. And this is a classical R matrix. So this is a slight generalization of what I was saying on the previous slides. This already includes deformations. So this already includes trigonometric or elliptic deformations, depending on the R matrix that you pick here. So this is the same R matrix that was studied by Belavin and Drinfeld in 1980. So for example, this is the trigonometric R matrix here. Its main property is the solution of classical Young-Baxter equation. This Lagrangian unifies all CPN, Grassmannian, flag manifold models, as well as their deformations. Now I will explain. So chirality, I told you it's a chiral model, yeah? So chirality is very important here. Maybe I should point out. So chiral here in principle can be thought of as just formally as meaning that there are these chiral projectors here. Because the most general invariant interaction would involve just arbitrary powers of psi's without these projectors. But here there are these projectors. And this is really important for it to be a sigma model, actually. This can be seen at the simplest example, which is the Thiering model, actually. And the first observation here is that, so I work on Euclidean worldsheet signature. So in Euclidean worldsheet signature, chiral symmetry is, as was observed again long ago, is actually a complexification of the original symmetry. So if you have U1 symmetry, chiral symmetry will be C star. Acting on these U and V variables, these are the Weil spinors, yeah, Weil components of that Dirac boson. They act by scaling U and V by opposite factors of lambda. Lambda is a complex number. That's chiral symmetry in Euclidean signature. And what it ensures is that the interaction is quadratic in U's and quadratic in V's separately. It doesn't have terms U to the fourth or V to the fourth, which would not be chiral invariant. And why is this important? So let's look at this example of Thiering model, this bosonic Thiering model. So V and U are just two singlet variables, yeah, two scalar fields, so to speak, bosonic scalar fields. And because the interaction is quadratic in U's and V's, for example, I can integrate out V. And I obtain a sigma model form of the Lagrangian. This is a sigma model with target space a cylinder. Yeah, this is canonical metric on a cylinder. This is a flat metric. You can, by exponential map, you see that it's a flat metric. So in this simplest situation, it's an equivalence between bosonic Thiering model and a free boson with a linear dilaton. So the linear dilaton you get because of the Jacobian here. There's some one-loop determinant. But the point is that this logic works in complete generality. So for all, if it's n component matrices, this U and V in the previous slide, still the Lagrangian is quadratic and U's quadratic and V's. You can always integrate out V, also in the deformed case, and you get a sigma model. For example, CPN model, Grossmanian model, flag manifold model, and so on and so forth. Okay. So these are the Feynman rules of this theory. So this theory, as you can imagine, is rather simple. It has this UV and U bar V bar propagators, which look like the fermionic propagators, Maslow's fermionic propagators, and a single vertex, which is given by the classical R matrix. For example, using this formalism, we can easily calculate the one-loop beta function of this model, which is just given by these two simple diagrams, and ultimately it just leads to this contraction of R matrices. There are two vertices, right? So you contract the R matrices, this is the beta function. So this allows, for example, to solve the Ricci-Flow equation very easily. So the Ricci-Flow equation, or renormalization group equation, in these notations, it just says that the derivative of the vertex, derivative of the R matrix, with respect to Ricci time, is the beta function. And the beta function is this quadratic combination from the previous slide. And I remind you that the R matrix, it depends just on one parameter, which is this deformation parameter that I called S. And this equation is just an ordinary differential equation, and it's a closed system. So remarkably, it's a closed system. So in principle, we have a huge number of couplings, right? We have quartic interactions, so we can have like n to the fourth number of couplings. But this is a one-parametric family closed under Ricci-Flow. And the solution is just S equals e to the n tau. N is the dimension of, so tau is this Ricci time. S is the trigonometric deformation parameter. This is in the trigonometric case. And n is the dimension of the ambient space, so CPN minus 1, or in what space our flags live. So this is a completely universal solution. So the beta function is universal for all of these models. The solution is also universal. This is a generalization of the old solution of Fatiev, Onofriy, and Zamolodchikov from '94, which is called sausage. So the sausage is a trigonometric deformation of a CP1 with this metric here. It looks like this green thing is supposed to represent this target space. And the length is proportional to log of S, the length of the sausage. So the parameter S is e to the 2 tau in this case, And it interpolates between S equals 0 and S equals 1. So S equals 1 is the undeformed sphere. Right? This is the usual metric on a sphere in stereographic coordinates. And there is this factor, vanishing factor, which means that the coupling constant grows. So it's an infrared limit where the coupling constant grows. And the ultraviolet limit is when an S is equal to 0 is when it's a cylinder. So it's a Ricci flow interpolating between the cylinder and the round sphere. And the interpretation of the cylinder, this is a flat cylinder. So its interpretation is that this is asymptotic freedom. So you interpolate between a flat target space and a non-flat target space. Okay. And the same thing, so this was known in '94, but basic generalizations of this was not known. So this is, like I say, this provides a generalization for arbitrary flag manifolds of this thing. Moreover, the solution is explicitly known. And in the simple case of CPN, you can also check that the Ricci flow interpolates between a round metric on CPN and the n-1 dimensional cylinder. So again, it's between flat space and this round CPN. So I should say that in principle you could integrate out these V fields and return to the geometric form of the model, right? With the B fields, metric, it should be a sigma model, right? And so we could, in principle, check that the Ricci flow, these are generalized Ricci flow equations, This is the beta function of the sigma model here, that they're satisfied. This has to work. So it does work, but it's way more complicated to check this. There's also a dilaton that arises in the process of integrating over V. So this is much more complicated, but, and there's really, as we see, there's really no reason to do that. It's much easier to work in this Gros-Neveu framework, but it can be done in principle. Okay, so now I'll pass to the subject of anomalies. So these models like CPN, for example, bosonic CPN model, they're known to have some anomalies since the 80s. These are anomalies in integrability charges. So these models are known to be classically integrable, but quantum mechanically there's some anomaly, which was found by this Abdallah and company in the Lucher's non-local charge, which is one of the generators of the Yangian of this model. So there is some anomaly in the Yangian of this model, which is an anomaly in integrability, in principle, in the bosonic CPN model. And it has been known that these anomalies can be cancelled by adding fermions in various ways. So now I will explain how this is can be easily explained in this setup. So the claim is that these anomalies in this setup are just the chiral anomalies of this complexified symmetry. So the chiral anomalies, it just basically comes from the effective action, so just from the determinant of this Dirac operator here, which was calculated by Schwinger in the 60s. It has this form, and this is a source of the anomaly, because it's not invariant under complexified gauge transformations. So it's gauge invariant with respect to the usual gauge transformations, which are the vectorial gauge transformations. But the axial gauge transformations are the complexified ones. And this has an anomaly. This is not invariant. So the Lagrangian is invariant, but the effective action is not invariant. That's an anomaly. And this anomaly is one loop, so it exactly comes from this determinant. And you have to do something to cancel it, because otherwise it's not a well-defined gauge theory. For example, you can add it just by adding fermions. Because you see the bosonic part looks like a fermion, right? This was the bosonic part. So I add the fermionic part in exactly the same way. And the determinants will just exactly cancel each other. So that means that, say, the coefficient here is 0. So the claim is that when you add fermions in this way, as to cancel these anomalies, the models are quantum integrable. Well, that's the conjecture. The key point is that in all these works in the 80s and so on, one always started with a compact gauge group like U1 here, and one imposed the condition that say the vector fields of the sigma model, the fields of the sigma model are normalized, like U dagger U equals 1. I showed you before. Here you uplift this condition and promote the gauge group to the complexified gauge group, and these are the anomalies of this complexified gauge group, which are not seen in in the old context. Okay, and so there is a generalization of this. So I told you that the sigma models are bosonic Gros-Neveu models. This may be a more physical kind of rewriting, but there's also a differential geometric rewriting of this thing. So the models of this type have two ingredients: the Liouville-1 form, which is like this kinetic term in the Gros-Neveu model, and the interaction term. So the setup is like this. You have a superphase space phi, which is a complex symplectic quiver supervariety. And you have matter fields UV in representations W and W dual of the complex gauge group G gauge. So the quiver varieties, they have gauge groups at each node. And the matter fields are matrices mapping from one node to the other node. These are these W and W dual. Then there's a global action of a complex group G global. So you can construct a complex moment map mu for the action of G global. That's a completely well-defined procedure. You have a symplectic space, you have an action of a group, you construct a moment map. And then you write this Lagrangian. So the interaction is just the coupling of two moment maps. And you have anomaly cancellation conditions, which say that the supertrace of two generators, a product of two generators of the gauge group is 0. This is the same as this cancellation of determinants on the previous slide. You remember that the effective action is quadratic in F, so that's the reason why there is this quadratic relation. And supertrace comes that, of course, you subtract the fermions from the bosons and so on. So the proposal is that this should be integrable models. And so some examples. So this is in the paper to appear. So the main example here is CPN model with fermions. So again, this old situation, but so how can we understand it from this standpoint? Again, back in the 80s, the main situations that were considered were minimally coupled fermions and the supersymmetric model. So the claim is that these two models have different phase spaces. They're just different phase spaces and different interactions, of course. But even the phase spaces are different. So in the case of minimally coupled fermions, the phase space is the cotangent bundle of V, where V is a configuration space, yeah, as usual. Yeah. V is a configuration space, and in this case, it's a kind of conifold bundle over CPN minus 1. So it's this vector bundle over CPN minus 1 with fermionic fibers. So pi just means that the fibers are fermionic. So the fermions live in the fiber of the vector bundle, and the bosons live in the base space CPN. So now if I take as this G, I have to construct a moment map to introduce interactions. So in particular, I have to pick a global group that acts on this phase space, yeah? So if I take SLN C embedded in PSL n/n and acting on the first vector SLN, yeah, with trivially on the second SLN, so it acts on CN0 but not on C0n, then I get these minimally coupled fermionic models. That's the definition of minimal coupling in a sense. I could as well consider other models, other couplings of fermions. For example, I can take as a global group 1 times SLN, so the other SLN. This is the one acting on fermions. In this case, I get the usual fermionic Gross-Neveu model. So I'm saying this step generalizes fermionic Gross-Neveu models and sigma models. And this is essentially the same thing. I could also consider the so-called CPN-1/n model, also considered in the past by various authors. In this case, I just take the global symmetry group to be the full group, symplectomorphism group, which is PSLN/n. I can also consider supersymmetric model. Supersymmetric model has a phase space cotangent bundle to V, where V is the tangent bundle of CPN. So in supersymmetric models, fermions live in a tangent bundle. And this can be written as a quotient of this kind of space with UV coordinates, super space, by this super gauge group. So this should be understood as obtaining worldsheet supersymmetric models from target space supersymmetric models. You have a model with target space supersymmetry, you gauge the target space super subgroup, and you get a worldsheet supersymmetry. Yeah, I wrote here superquiver, so this naturally suggests the idea of considering superquivers, more general than this one drawn here. So finally, I will summarize the whole idea of this approach is to consider integrable sigma models beyond symmetric target spaces. For example, flag manifolds models and similar models. There's also, there's a GLSM formulation, like I explained, beyond Kähler target spaces. So then the main claim is that sigma models are gauged chiral Gross-Neveu models, bosonic, fermionic, mixed, so on and so forth. This is a very useful approach because, for example, a beta function can be computed really easily without any complicated target space, whatever Ricci curvature, and so on and so forth. Then you can solve Ricci flow equations. And then there are some anomalies, and the anomaly cancellation leads to the idea of super phase spaces. There is a new way of obtaining supersymmetric Lagrangians. And I should say there are some other technical benefits. For example, these models are ultra-local, so there are this problem of non-ultra-locality in sigma models. Here it's not a problem, they're ultra-local. Moreover, the interactions are polynomial. So these are models with polynomial interactions. There are no nonlinear constraints, basically. You have models with polynomial interactions. And one explanation is that, for example, in simplest case, it's known that it's a reduction of general relativity in Ashtekar variables. That's kind of a funny connection, but Ashtekar variables are known to make interactions polynomial in GR. So same thing applies here. So, okay, ultimately, I think this will lead to the solution of these models from first principles, but so far it's a proposal for the differential geometric description of these models. Thank you very much.
Thank you. We have time for one or two short questions. Yes. You seem to switch between these different descriptions quite freely. And as far as the classical analysis is concerned, I agree. But what about the quantum level? I can imagine that they are not equivalent. So the correct definition is using the Gross-Neveu model. That's the first principle's correct definition of sigma models. For example, the dilaton that I showed is there. Yeah, the dilaton. The dilaton arises from integrating out the V field. So from going back from the Gross-Neveu description to the sigma model description. That you would not be able to guess it directly from the sigma model description. And it's a non-trivial function, and it has to be there to match the RG flow. So yeah, and this moment map description is equivalent to the Gross-Neveu description. That's just a generalization to other. It's like more species of bosons, fermions. It's a generalized Gross-Neveu system, so to speak. So this is the correct quantum, the one that should lead to a correct quantum theory, let's say.